Okay, folks, it's time for our next online lecture. And so today we're going to talk about three things. I've listed them here. The first is electromagnetic waves, the orientation of the various components, the electric field, magnetic field, and wave vector. The second thing will be to talk about average quantities of power, momentum density, and energy density. And the third thing will be the effect of materials, namely the index of refraction. And I'll put two breakpoints between these. I'll put a breakpoint between item 1 and 2 and a breakpoint between item 2 and 3. So those are the times that you could take a break and come back to those sections. Okay, so let's remember what we were talking about last time. We were talking about waves. Yay, waves, electromagnetic waves. But waves are a very general phenomenon, and so last time we had a very general discussion. I'm not going to go through that all again, but I'll just remind you that the wave equation is when we have some quantity, u, it could be anything, really, the vertical deflection of a string, or the pressure compression of the atmosphere. It could be anything, or it could be an electromagnetic field. The point is, if the second derivative with respect to time of this quantity is proportional to the second derivative with respect to space, then that's a wave. Then that quantity can behave like a wave. And the proportionality constant, of course, is the velocity squared. So that is the wave equation. And the solution to the wave equation is, in general, any function f or g, any function, but we can make these, but we put into the argument x minus vt or x plus vt. So that's the right moving wave, and that's the left moving wave. So these are the solutions to that equation, is a right moving wave or a left moving wave. And so really we can pick any function f or g, but we have some favorites. And really our favorite function, or the most physically relevant function, would be this one, f of, let's say, if I let gamma equal x minus vt, then f of gamma would be a sine k gamma. This is a sine wave, so then my wave is can be written like this: a of sine k x minus vt, which is equal to our favorite thing, which is a of sine kx minus omega t, where now we have defined kv equals omega, or in other words, v equals omega over k. And this is our favorite wave, the sine wave. We all know and love the sine wave. And we have the wavelength, lambda, that's my lambda. And we know that k is equal to 2 pi over lambda. And we know that I can also think omega is 2 pi frequency. If you want to think in terms of time, that's the, which is equal to 2 pi over t, the period. So these are familiar behaviors of the sine wave that you've seen in other classes, I think. And so this is a very, but I just want, the thing I want to emphasize is this is just one particular solution. There are many others, but we like this one a lot because it's easy to make in real physical systems. It's a nice solution because we can use it as a basis state. We can construct other waveforms from it. Can construct other waveforms using Fourier transforms and whatnot. And it's the solution of a simple harmonic oscillator. Solution of SHO. And so often charge in a material is like a simple harmonic oscillator, and so then it often leads to waves, to sine waves. So that's why we love the sine wave. But but mathematically, our favorite wave. Physically, the sine wave is our favorite, but mathematically, our favorite wave is this one. F of gamma is equal to a e to the I k gamma. And the reason we love this function is because it's mathematically so simple. So then now we have a wave u of xt is equal to a e to the I kx minus omega t. So this is really our favorite wave, our mathematical expression. So this one we love because of the math is easy, but physically we have to always remember the sine wave is more physical. So the physical wave is that the sine wave, a sine kx minus omega t, is equal to the imaginary part of this one, a e to the I kx minus omega t. So these are just little things that we have to remember, that we always have. If we're using these imaginary waves, then we have to take to make them physical, we have to take the imaginary part of them. Okay, well, that's just a little bit review. You'll see how that works. If that is confusing to you, don't worry. It should come out when we do some more examples. So let's apply this to E and M. And now let's apply these concepts to, because those are just math concepts really. Let's apply to electricity and magnetism. And so for electricity and magnetism, what we found last time is that the electromagnetic fields, either E or B, both satisfy the same wave equation. It's equal to the velocity squared times the gradient squared of E or B. So we get the same wave equation for E or B, where C squared is equal to 1 over mu naught epsilon naught. And so we see then that the speed of light, C, is 1 over square root of mu naught epsilon naught. 3 times 10 to the 8th meters per second. Okay, so that's what we did last time. And so now we want to take a look at the solutions of this wave equation. And so we see, and so let's consider our favorite. So physically then, a very nice solution. So physically, our favorite wave is this one, the sine wave. And remember, this is just one solution of the wave equation, but it's our favorite solution because it's so useful for so many things, and simple harmonic oscillators follow this relationship. But the sine wave is this. So we see that this is one solution of the wave equation, is that E of xt. Well, let's do it. Let's make it more general. E of rt is equal to some vector, the amplitude, times sine of k dot r minus omega t. Okay, so this is an electromagnetic wave. It satisfies the wave equation, and so this is one of many types of waves, but this is really our favorite one. And so let's take a close look at this one. We want to take a close look at this one. Closer look. And so what I'm going to do is I'm going to quickly jump into because we're going to do some math on this, and so let's quickly jump to let's make the math easier. The math is easier if instead of looking at this is the physical wave, but mathematically I can represent it with this. I can say, and I keep harping on this because I remember when I was an undergrad, I found this confusing, that, how you would go from a real function to an imaginary to a complex function. But the math is just easier. If we can represent this very same wave with this. We can call it this. We can say that it's a complex wave minus omega t. So we use the complex exponential. So we're talking about the same wave. So this is the same thing, and we'll do the math. But then at the end, we have to remember that the physical E, the actual electric field, is equal to the imaginary part of this. But this last little step, we take the imaginary part, we often skip it or just don't worry about it, or we do it at the very end. But this is the physical electric field, is the imaginary part of this one. Okay, so let's just we'll use this one to do all our math because it's so simple to deal with. Okay, so let's assume that we have an electromagnetic wave, and let's assume that this is my electromagnetic wave. It's this type of wave, and what do we call this? We call it a plane wave. It's a plane wave. And so why is it a plane wave? And so this is why it's a plane wave, because if I was to try to plot that function out, then what you would see is that you get these planes. And they're moving in a direction K. And the planes are perpendicular to K. This is a right angle. And what are these planes? I remember I was confused by this as an undergrad, because they call it a plane wave, and you're wondering, what the hell are the planes? What is the plane of a plane wave? What are the planes? And so the point of the plane is that they are planes of constant phase. The planes are geometrically planes of constant phase. Because what we have is the electric field, if it's a plane wave, then you have this e to the I, e to the I k dot r minus omega t, and this is the phase. And the phase is a function of position and time, and the phase is moving forward. As I move in space, the phase gets bigger from this. As I move in time, the phase also changes according to that. And so if I let's freeze time. Let's freeze time t equals 0. So let's freeze time to t equals 0, and then we see that E is equal to, I'm sorry, that's E naught times e to the I k dot r. And so now we see that this is the phase, and the phase is a function of position. And so if we plot the phase, then we see, if we do look at the geometry, then we see that that's the k. If the wave is moving in some direction k, and then we notice that if I look at every point on this plane, pick these r's, where these are different r's, no matter which r I pick, then the phase is constant on this plane, because the phase phi of r is equal to k dot r. And so if I pick some point as the origin, then at every point on this plane, k dot r is constant. And look at the geometry. Do the geometry yourself. This is k, this guy. And so k dot r is going to be this distance for all of these different r's that I pick. And so every k dot r is constant on the plane. So equals constant on plane, and that plane is perpendicular to k. So if I pick any plane perpendicular to k, then the phase is constant, and so that's why we have we call it a plane wave. And so then if we it's convenient to pick these planes of constant phase, and then we notice also that if this is the direction k, then if this is a distance lambda, then the phase is the same. So phi here is the same as the phase on this plane. So the phase is constant on this plane everywhere, But if I go to another plane here, the phase will be different, and here it's different again. But if I go to this point, then the phase is back to constant. And the way we usually represent this, this is usually represented in this sort of other way of doing it when we just plot this, and you can just see that, you know, this phase is the same as this phase. But this is the three-dimensional representation, 3D representation of this. And so that's why we call it a plane wave. These are simple things that you might have seen before, but I know they kind of can be confusing too. And so sometimes the simple things can be the most confusing. Okay, so we see that we can then have a plane. So when I draw this, E is equal to E naught e to the I k dot r minus omega t. What I want you to think of is a plane wave that's traveling in the direction of k. And then you can think of these planes like this, these planes of constant phase. And really, you can think of really what's happening is that the electric field, let's see if I can draw this right. This is the electric field. The electric field is oscillating, and so this is the, I'll draw it like that, that's the E. And so you can see that the electric field here, it's plus, minus, plus, minus, plus, minus. So the electric field is oscillating. Here the electric field is pointing down, here it's pointing up, down, up, down. So this is the picture you should have in your head of the plane wave. It's very important that you have this picture in your head. You have to understand the geometry so that this is not just some crazy equation, it's a physical object. This thing is that thing. You should have that picture in your head. I think that really helps. But we also know that E is not only the only solution. We also can have a magnetic field. And we also can have a magnetic field plane wave. Because this is also a solution of the wave equation. So we see that this is also a solution of the wave equation. So the point is that we then have these three important vectors. And we got them from the wave equation, because these are the solutions of the wave equation. And the three important vectors are E, B, and K. These are vectors. And so what is their relationship between them? Relationship. We know that we can have a plane wave in the electric field, and we know that we can have a plane wave in the magnetic field, and we know that because they are solutions of the wave equation. But what is the relationship between them? Is there constraints on E and B and K? Are there constraints? Are they related to each other in funny ways? Are they? Well, let's answer that question. And the way we answer that question is by using Maxwell's equations. So the constraints on the various components of our plane wave, the constraints on E, B, and K come from Maxwell's equations. Maxwell's equations. And it's really easy to see that. And let's see that now. So for example, let's ask a question. Let's ask question number 1. Here it is. What is the orientation of E naught relative to K? And this is not a trivial question. I have here my plane wave, E equals E naught times E to the I K dot R minus omega t. That's my plane wave. That is a solution to the wave equation. So this is good. It solves the wave equation, so it's a good wave, but does it solve Maxwell's equations? Solve Maxwell's equations. It might not. Now, that can be confusing to you because we use Maxwell's equations to get the wave equation. But remember, Maxwell's equations gives many constraints, and so I could have solutions to the wave equation that are not necessarily solutions to Maxwell's equations. What I mean by that is that I cannot choose any value of E naught and K. I can only choose special ones. There are only special ones that satisfy Maxwell's equations. And let me show you how that is true. It's really quite simple to see. You'll see that in a moment. Let's consider this Maxwell's equation. So if we have a wave in a vacuum, then Maxwell's equation, then one of the Maxwell's equations is del dot E equals what? Well, normally we would put rho there, rho over epsilon naught, but because we're in a vacuum, there's no charge density, so it's 0, because there's no charge density, Rho equals 0 in a vacuum. There's nothing there, and so there's nothing that creates divergence in the electric field. So del dot E is 0. That's Maxwell's equations. That's a Maxwell equation. Okay, well, let's apply this to our wave. So let's plug in our wave. Plug in wave. And this is really simple. All these constraints we get by just plugging the wave into Maxwell's equations. So let's just plug in the wave. So we see that del dot E, but now the E of the wave is this. E naught E to the I K dot R minus omega t. And that has to be 0. For this wave to solve Maxwell's equation, del dot that has to be 0. Okay, well, let's do it. So what happens when I do del dot this complex exponential? Now you see the power of complex exponentials. It's really simple because since it's an exponential, I can just pull the exponent down. So when I take del dot of this, I know that it's going to be, if I have del dot some E to the I f of r, then this is equal to E to the I f of r times del dot I f of r. That's the beauty of complex exponentials. So simple. So then we see then that the divergence of this is equal to E naught E naught f of r. Let me get all of this straight. Sorry, I just want to make sure that I get all these things correct. So then this is, so del dot, so if I just take the divergence of this quantity, then what I get then is that quantity, E naught times E to the I K dot R minus omega t, dotted with the I K, because the gradient just what it does, it just pulls out this spatial part. And so I basically can, maybe I did a bad thing of this. Like basically if I do del dot some E to the I, then basically what I'm doing, I'm getting lost in the math here, but basically you just are pulling down I times K. So that's just the gradient of this comes out. And so the gradient is replaced by ik. And so the math is really simple. And I'm sort of screwing it up right now because sometimes I screw up math in real time, but it's very simple math. And so you guys just sit down and figure it out on your own. It's trivial math. It's just the derivative of exponentials. So that's why it's so simple. And so this then is equal to 0. And so now what I have from this equation then is I can divide out. Now I can divide this out, and I have k dot E naught is equal to 0. So that's what we get from this, from the del dot E equals 0, becomes k dot E naught equals 0. And so this then tells you that k is perpendicular to E naught. And that's a really important constraint. That means then that the E field is the electric field part of an electromagnetic wave is transverse. It's a transverse wave. And so that means then that the E field, that means that if I have K in this direction, we've just proven that this polarization, E naught, has to be perpendicular to it. So that's E naught. Because remember, the electric field is E naught e to the I k dot r minus omega t. And so this is the polarization. And so the polarization of the wave we see has to be perpendicular to k. And that's an important constraint. For example, could I have a wave that looks like this? Could we do this where I have k here, and then I have my polarization pointing in that direction, and then my wave going like that, but with the polarization that's pointing sort of off to the right like that? And the answer is no, can't have it. At least not in vacuum, not in vacuum. Maybe in some weird material you might have something like that, but not in vacuum. Because we had here, because del dot E, we say not in vacuum because del dot E equals 0 means that k dot E equals 0, which means then that k and E are perpendicular. So the lack of any material in the presence of the wave means that the wave has to be transverse. So, and that's a simple thing to see. The math is simple. I'm sorry that I screwed up on that up here on this derivative. I sometimes screw up on simple math, but you guys should just do it on your own and see for yourself. Okay, so now let's do the same thing. Now we can also see, what about the B field? What about the B field? Well, we know for the B field is also a wave. So we know that the B field part of an electromagnetic wave can also, this is a solution. It also can act, it also is a wave. This is also a solution to the wave equation. Solves wave equation. But what's the constraint between B and K? Is there a constraint? And the answer is yes, there is a constraint. And that constraint, of course, comes from Maxwell's equation. And of course, here, the Maxwell equation, let's look at the divergence of the B field. What is the divergence of the B field? Well, we already know, since there's never any magnetic monopoles, this is always equal to 0. And so let's do it. So let's find the constraint on the B field. So we do del dot B naught, where that's the polarization of the B field, e to the I k dot r minus omega t. And now when I do del dot on this complex exponential, you see that something really beautiful happens. It just pulls out the ik. I can replace the del with the ik, and I get ik dot B naught e to the I k dot r minus omega t. This is why we love the complex exponential. The math is so simple. See, I just replaced the del with ik. That's why we love these complex exponentials. And so this equals 0. And so then you can see that k dot b naught equals 0. And so therefore k and b naught have to be perpendicular. So we see that b is also a transverse wave, is a transverse wave in vacuum, meaning that the polarization, it has to be perpendicular to the direction. So if this is the direction k, in this direction to the right, then the polarization has to be perpendicular to the direction because of Maxwell's equation. Del dot B equals 0. Okay, great. So now we've learned that for these simple plane waves, so what we've learned is that for a plane wave, which is really our favorite kind of wave, and there are other ones too, all waves are not plane waves, but it's our favorite one. For plane waves, we just learned that the electric field is perpendicular to K, and we've learned that the B field is perpendicular to K, where K is the direction that the wave is traveling, that the plane wave is traveling. But now we can ask, what about the relationship between E and B? What about E and B? Is there a relationship between them? What are the relative directions? What are the relative directions between E and B? What is the relative orientation? Orientation of E and B. Because remember, a plane wave, an electromagnetic plane wave, you have both E and B at the same time. So it's kind of a complicated beast. And so what is it? What is the relative orientation of E and B in an electromagnetic plane wave? Well, let's, how do we find that out? Well, let's just use Maxwell's equations. It's so simple. Use Maxwell's equations. And the one that we're going to use, there's different ways to do it, but let's use Faraday's law. Del cross E equals negative dB dt. Faraday's law. And we use Faraday's law because it has both E and B in it at the same time. And so let's just plug in. So any solution, so any electromagnetic field that we have has to satisfy Maxwell's equation. So if we have plane waves, then they gotta satisfy this equation. So let's see if this places a constraint on E and B. So this is a constraint. This equation places a constraint on E and B. And so to see what that constraint is, let's just plug in the waves. It's so simple. You have it. Basically, Maxwell's equation gives us a differential equation, and we're just plugging a solution into this differential equation. And so here we'll plug in here e to the I k dot r minus omega t. We'll plug that into the e part, and for the b, we'll plug in b naught e to the I k dot r minus omega t. And we'll plug them in. And this is really nice. And so now we see the power of the complex exponential, because not only does it make taking the spatial derivative simple, but it also makes the time derivative simple too. Because what happens is we see that the del is going to get replaced by ik, and we see that the ddt is going to get replaced by, when you take the time derivative, the ddt is going to get replaced by negative I omega. You can just see it right here, because in front of the r, I have ik, and in front of the t, see, in front of the r, I have ik, and in front of the t, I have minus I omega. So now that makes the math really simple, because now this part turns into I k cross E naught, e to the I k dot r minus omega t, and this derivative turns into, I have minus, and then I have the derivative turns into minus I omega times B naught e to the I k dot r minus omega t. Okay, and so then what we get is we see then that these, let me make sure I did the math right, yeah. So then we see that these guys turn into a plus, and we see that the i's cancel from both sides of the equation, and then we see that we can cancel this from both sides of the exponent, we can cancel from both sides of the equation, and what we're left with is k cross e is equal to, k cross e naught is equal to b naught. So we see that the polarizations have this very special constraint between them. And what does that say? Well, that tells us right away that we see that B naught is perpendicular to E naught. Oh my God. They're perpendicular. They have to be. Because we see that, because it's a cross product. So B naught has to be perpendicular to both of these guys. So we already knew that B naught's perpendicular to K, but now we see that B naught is also perpendicular to E naught. And there's a right-hand rule relationship buried in there. To see that right-hand rule relationship, okay, well, there it is right there. You can see B naught is equal to K cross E, so you can get the direction from the right-hand rule of B naught relative to E naught. But there's a nice relationship that I personally like a lot. Oh, I'm sorry. Let's see. Did I leave out? There's a little omega there. Sorry. There's a little omega there. That doesn't change the directions because omega is always positive. Okay, and so let's take a closer look at this equation. And so if we look at this equation, one of the things that we can do is we can do this. We can say that we can write K is equal to the magnitude of K times the direction of K, K hat. And so if we do that, then we can rewrite this equation as B naught is equal to B naught is equal to K over omega times K hat cross E naught. Okay, just a very simple thing I did. I just brought the omega down under and did this little substitution. And so then that's quite nice because we then notice that remember omega over K is equal to the velocity of the wave, and we know the velocity is c, and we know that c is equal to 1 over square root of mu naught epsilon naught in vacuum. I keep stressing in vacuum because eventually we're going to take it out of the vacuum, but right now we're still in the vacuum. And so then I can see that I have this nice relationship, which is that the polarization of the B field, the amplitude, is equal to B naught is equal to 1 over C, because that's what this is right here. That's 1 over the velocity, 1 over C times K hat cross E naught. And one reason why, and this is a very nice equation because these quantities are all perpendicular to each other, and so then I can just, because everything is perpendicular, the cross product is simple. There's no sign, you remember, if I have A cross B, it's equal to A magnitude times B magnitude times sine theta. But if the quantities are perpendicular, then sine theta is 1 for 90 degrees, and it's just, so the magnitude of A cross B is just A times B for any two vectors if they're perpendicular, if A perpendicular to B. And so here we can take the magnitude of both sides, and then that leads us to this very nice relationship, which is that B naught, the magnitude of the amplitude of the B field wave is equal to 1 over C, and this is a unit vector, so that the magnitude of that is just 1 times E naught. So we get this very simple relationship, and this came from Faraday's law. That's where this came from. We plugged the wave we plug the E and B waves into Faraday's law, and so we see that Faraday's law, the Maxwell equation, tells us that there's this very simple relationship between B naught and E naught. So we see that we see that the B field can be written in terms of the E field. There's this important relationship between them. So these are constraints. So we see that not only is the B field part perpendicular to the E field part in a plane wave, but we also have an important relationship between the magnitudes of these two quantities. Okay, and so now let's take another. There's another important relationship that I really like. Let's consider, for example, let's consider, for example, this relationship where I have, let me get it right. So here I'm going to have, let's take this relationship where I have B naught is equal to, well, let's just take it here. Let's see, I have B naught, or let's see, where do I want to take this from? So let's go back to this relationship up here, and let's bring it down here. And here I have omega B naught is equal to K cross E naught. And so what I want to do is let's just derive one more constraint on the directions, and let's do it this way. So this is what we got from Faraday's law from back up here, as you see. And what I want to do is let's cross it with E on both sides. Let's do E cross on both sides. And so then what I will do is, if I have if I cross both sides with that, then I can have omega E naught cross B naught. We're going to do E naught we're going to cross it with E naught on both sides. So E naught cross B naught, and then we're going to do E naught cross K cross E naught. All right, so let's do this, and we get something really useful from this. And so when we do this, we see that this is just the double cross product, and we know what that is. That's equal to K times E naught dot. So this is just a vector identity that you guys have all used before, minus E naught times E naught dot K. Right? That's just that cross product. But this E naught dot K, we know what that is because the electric field is perpendicular to the direction of the wave. And so this has to equal 0. And so then what we have is we just get this side, and that side is K times E naught squared is equal to omega E naught cross B naught. And so then we get this very nice relationship, which is that K is equal to omega over E squared, E naught squared times E naught cross B naught. And this is a very famous relationship, which I really like because this gives you a nice sense of the direction. So the direction of an electromagnetic wave, a plane wave, the direction K of a plane wave, of an electromagnetic plane wave, always points in the direction, it always points parallel to this, parallel to E cross B, or E naught cross B naught. If you take the electric field and you cross it with the B field and use the right-hand rule, that is the direction of the plane wave. And so that's I find that to be very helpful. It really helps you to see all the directions. And it's really quite nice because it makes sense also too, because you guys remember that the pointing vector S is equal to 1 over mu naught E cross B. And this is the flow of energy. That's the flow of energy. And so everything kind of hangs together, because this is the flow of energy is equal to energy flux equals energy density times velocity, because that's what a flux is. It's a density times a velocity. And you can see that you can see now that for a plane wave, then you can see immediately that the S, the pointing vector, should have said S is the pointing vector, I'm sorry, pointing vector. We see that S is proportional to K. And that just makes sense, because if I have some plane wave, there it is, it's traveling, then I see that the plane wave is traveling in some direction K, and so the energy flows in the direction of the plane wave. Energy flows in direction of K. And that should be very intuitive and logical. So if a plane wave is moving in some direction, then the energy is also flowing in that direction. So that's why I think this is a really nice relationship to try to understand. Okay, so now we're ready to write down the actual plane. So now we really understand electromagnetic plane wave. So the electromagnetic plane wave, we really understand it now. And this is what it looks like. So if I have some wave traveling in this direction, then I see that I can draw it like this. Let's see if I can pull this off. I'm not sure I'm gonna. There's a special way to draw it, and then I can draw it, and then this is the E field. That's the E field, and I'm drawing it in a funky way, but you'll see it. I'm trying to draw it three-dimensionally. That's why it looks funny. Let's see if I can draw it. I'm trying to make it look three-dimensional. That's why it's so screwed up. And so here, so this is the E field up here. I'm trying to draw the E and the B at the same time. This is the E field. And then this is the B field. And so the B field is like, I'm not sure that my drawing really is working too well. Let's see, E. Yeah, I'm not doing too good a job here. But the point is that they're perpendicular to each other. I was trying to draw that. Not sure that I really pulled it off. But I think you guys have all seen this picture in books. You should go look at it in a book. The idea is that these are happening at the same time. And this is really important to understand, that the E and the B are happening at the same time in a plane wave. And that's what we just derived. We just derived all these relationships. I'm trying to represent them graphically. But it's hard. These pictures are hard to draw. But I want you to see that they're perpendicular. It's hard to do. It's hard to draw it because it's a three-dimensional object. But the polarization of the wave, for the polarization, it's conventional to say that the polarization it's conventional to pick the polarization direction using the E field. The polarization is in the direction of the E field. E naught is equal to an amplitude E naught times a unit vector n, and the n the n hat is the polarization direction. Polarization direction. It's the direction in which it's the direction of the polarization of the E field, where the E field is, for this we have E equals E naught e to the I k dot r minus omega t, and we have B equals B naught e to the I k dot r minus omega t. And we've just derived all the constraints on E and B, E naught and B naught, and K naught and K. And they're all represented in this picture, which I didn't do a good job. But you have to see how E naught is perpendicular to B naught is perpendicular to K. And there's a right-hand rule relationship between them, such that K is proportional to E cross B. Okay, and so this then is a good breakpoint. So this is a breakpoint. So breakpoint. So this is a time when you can go do something else and take a break and then come back, because this is a natural division point in the lecture. But I'm going to just continue. But the point is that you can go take a break now and then come back, because that was one logical unit of this lecture. So now I'm going to go to the next logical unit, which is to discuss what is the magnitude of the power carried by an electromagnetic wave, EM wave. What is the magnitude of the power carried by EM wave? Okay, so so let's suppose that we have an electromagnetic wave, plane wave, and so for a plane wave, let's suppose that we have let's consider an electromagnetic plane wave, like what we just had, like what we were just talking about. Consider an electromagnetic plane wave. And when we're talking about an electromagnetic plane wave, it has two parts. Remember, this is the electromagnetic plane wave. E equals E naught, e to the I k dot r minus omega t, and B is equal to B naught, e to the I k dot r minus omega t. So when I talk about an electromagnetic plane wave, it's both of these things at the same time. Both at same time. And there are special relationships between E naught, B naught, and K. That is what a plane wave is. Okay, so all those relationships we just derived a moment ago. Okay, so suppose I have a plane wave, this object, this funky object that I just tried to draw a picture of here. This is the plane wave. Plane wave, that's what this thing is. So suppose I have this funky plane wave that's traveling through the air, and then we know that an important relationship for the plane wave is that the magnitude of B of the magnetic field is equal to 1 over C times the magnitude of the electric field, the amplitude of the electric field, where C is equal to the speed of light, 1 over square root of mu naught epsilon naught. Okay, so let's now ask ourselves, let's ask ourselves a question. What is the energy density of the electromagnetic plane wave? Energy density. Now, you guys know what the energy density of an electromagnetic field is. We've already derived it. You know that the energy density, U, of an electromagnetic plane, of any electromagnetic field, the electromagnetic energy density is of any electromagnetic system is this. We derived it. It's 1 over 2 epsilon naught times E squared, which could be position and space dependent. I'm sorry, position and time dependent. That's the electric part. That's the energy density carried in the electric field, but there's also some energy density carried in the magnetic field, which we derived, which you remember, which is going to be b squared, the amplitude b, the magnitude squared b of x and t, position and time. And so this is the magnetic part. And so what we want to do is that this is quite general, but we see that for a plane wave there's something very special, because for a plane wave we have a very special relationship between B and E. We know that B naught is equal to 1 over C E naught. This is a very special relationship for plane waves. And so let's see what happens for plane waves, because for a plane wave, we see then that this special relationship tells us that the magnetic energy density, which is 1 over 2 mu naught B naught squared, is equal to, I can replace the B naught with 1 over C E naught. And so I can just put right here 1 over C E naught squared. And so there's some simple little relationships that pop out from this, because now I can see that this is 1 over 2 mu naught C squared E naught squared. But we know that C squared is equal to 1 over mu naught epsilon naught. So then I can see that the magnetic energy density is equal to 1 over 2 mu naught times 1 over mu naught epsilon naught. Oops. Let me erase that. This C squared is on the bottom, and so the mu naught epsilon naught go on top. So it's mu naught epsilon naught times E naught squared. And then I see that these guys cancel. And so then I see that the magnetic energy density is equal to 1/2 epsilon naught E naught squared. And you think, hey, that looks familiar. Hey, something funny's going on here. Well, the funny thing is that this is exactly the magnitude of the electric field energy density. Oh my God. And so that tells us then that the magnetic energy density is equal to the electric field energy density for a plane wave. This is not always true for any electromagnetic situation, but it's always true for a plane wave. Plane wave. And so that means then that the total electromagnetic energy density of the plane wave is equal to twice the electric field energy density, which is simply equal to epsilon naught E naught E naught squared. And so, but then we see that but we can see then that the electric field, the actual electric field, is the physical electric field. Now let's talk about the wait, no, we're not ready to do that yet. Let's so what we can do next then is we can then, so this is the so this is our electromagnetic energy density. So that's a nice relationship for plane waves. Electromagnetic plane waves. But now let's consider, now what we want to do is we want to know the power carried by a plane wave. Power carried by a plane wave. And we know how to deal with that, because the power carried by a plane wave is going to be described by the pointing vector. And the pointing vector is of course this. S is equal to 1 over mu naught E cross B. And so what I can do is I can write, what we can do then is we can ask ourselves, what's the magnitude of it? Let's take the magnitude of these quantities, and that's S. And so we can see that the magnitude of the pointing vector, S, which is equal to the energy flux of the plane wave, remember, and that's going to be energy per time per area, is equal to the magnitude here, which is 1 over mu naught. And because E and B are perpendicular to each other, I can just write it as this, E times B. So the magnitude of the energy flux carried by electromagnetic plane wave is just the electric field times the magnetic field. And so, but then we can notice that the magnetic field, I can get rid of that part because I know that I can write the magnetic field, this, I can always write it as 1 over C times E for a plane wave. That's a relationship that is true for a plane wave. It's not true in general for every type of situation, but it's true for plane waves. And so then I can see that the energy flux of a plane wave is equal to 1 over mu naught C times E squared. Very simple little relationships. And then we can play a little math game, which is quite useful. We can let's just play a little math game. Let's just multiply by C over C times 1 over mu naught C E squared. And so then what we get is that this is equal to C times 1 over mu naught C squared times E squared. There's lots of little games like this that we can play. They're simple games, but I know it's sometimes hard to follow all the little steps. But let's just go with it. And then we know that this C squared is equal to 1 over mu naught epsilon naught. So we'll replace the C squared with that. And so this is equal to C times 1 over mu naught times mu naught epsilon naught times E squared. And you can see that these things cancel. And so I see that the power flux is equal to C times epsilon naught E squared. And this is a really beautiful relationship. I find it very helpful because what we see is that this is an energy flux, and we see that this is the velocity, and we see that this is the energy density. And this is really great because we know that in general, flux is equal to velocity times density for any flux. For example, where I could have a current flux, J, is equal to V times rho. Rho is the flux of charge, is the density of charge. So that's the velocity of charge, and this is the velocity of charge, and this is the density of charge, charge per volume. And so now what we have is that we see that S is equal to C times the energy density of the electromagnetic wave, where this is the velocity and this is the energy density. So this is velocity times energy per volume. So this was an example, analogous, but this is what we've just derived. This relationship. So the energy flux is equal to velocity times energy density. Okay, and so but energy flux, and so we can think of that as so what we can, so this is very visual, because what we see is that if I have if I have S, the energy flux, which is already here, energy flux, but that's also the power per area. And so that's the power per area carried by the electromagnetic wave. That's what S is. And so if I have the electric field carried in a plane wave, then the physical electric field, now I'm going to go back into the sine wave, the physical electric field looks like this. E naught sine k dot r minus omega t. And this might be confusing because, sometimes we use complex exponentials and sometimes we use sines and cosines. Here I'm using here I'm actually going to calculate an actual physical quantity so that you might measure in the laboratory, so I got to make sure that it's useful for me now to do it with the sine waves. So I want you to picture this, because if this is my wave, then you can see that the power S, the energy flux is a function of position and time, because my wave, my electric field, is a function of position and time. And so S of xt you can think of it as c, which is the velocity, times this thing, which is this other part, the energy density, which is epsilon naught E naught squared sine squared of, and now I'm going to write it kx minus omega t. And I can always replace k dot r with kx, because I will just pick my x-axis parallel to k, and that allows me to simplify the math. So you can always, an electromagnetic wave, we can always think of it as sort of as a 1D object in a sense, even though it's intrinsically three-dimensional, but the variation is in one-dimensional function. It's just because the k dot r I can always replace with kx. Okay. So the reason why I brought this up is because I want you to sort of visualize it, because this is the power carried by the electromagnetic wave, power per area. And so the way to think about it, and this is the velocity, and this is the energy density. And so the picture that you should have in your head is that you should picture this energy density, and the energy density is like this thing. There's energy, but the energy varies with this sine squared. So think of it kind of like this. So this would be my electromagnetic wave, my E. But because I'm squaring this, I have it squared, so that means that it's going to be the same on both in both halves of the. Even though this is the wavelength, I'm going to get the same amount of energy from both sides, from both halves of the wavelength. It doesn't matter whether it's positive or negative. So this is how you can kind of picture it. This is the picture I like to use in my head. And so this thing, so the electromagnetic field is like going, up and down. It's it's going. So this is the electromagnetic field. Drawing these is a pain. I won't draw them all. Okay, so this thing, this energy wave, these energy packets are flying through the air in some direction k. And if I'm standing here, there's me, and I'm holding up my hand, I'm saying, stop, you must practice social distancing, stop. And so then the electromagnetic wave is going to hit my hand. That's my hand. And so what I'm going to feel in my hand is going to feel, you can see it's going to be hot, cold, because what's going to happen is these I'm going to get a packet hitting my hand, and then there'll be nothing. So this is a max, but this is a node. So when a max hits my hand gets hot. I absorb that energy. But when the node hits my hand, I don't absorb any energy. So you can see that the power absorption in my hand is going to be, if I look at the power, it's the energy per time that I absorb, it's going to go up, down, up, down, up, down, up, down, like that. So it's going to oscillate. It oscillates very quickly. How quickly? What is the oscillation of the power that my hand feels? How quickly does it oscillate? How quickly does it oscillate? Well, that's a good question. We should just consider it for a moment. I think you guys know the answer. It's just the frequency. It oscillates with the frequency of light. A frequency is equal to omega over 2 pi, which is equal to 1 over the period, where that's the period. And so that's how quickly it oscillates. That's the frequency, how many times per second. And so we see that for light, what is the frequency? Well, it depends. There are different frequencies. I can have different types of electromagnetic radiation. So electromagnetic radiation is we have all possible frequencies. All possible frequencies. It can be anything. But there are some very important frequencies in our physical world. For example, probably the most important frequency is light. That's the one that comes out of the sun. And so for light, what we call light, that's a type of electromagnetic wave, then we know that that is an electromagnetic wave whose frequency lies right around. There's a range of frequencies, but it's lying all around this frequency, 10 to the 15th hertz. That's a frequency of visible light, like a green light is right around there. And so we then can see that for light, for this particular electromagnetic plane wave, then we have we can calculate the wavelength, which is, if we play with those little equations, we get it's c, it's the velocity over the frequency, that's the wavelength. And so that's going to be the velocity is 3 times 10 to the 8th meters per second, and the frequency is 10 to the 15 hertz, and so that leaves me with, if you work out the numbers, 0.3 microns, 10 to the minus 6 meters, 0.3 microns. So that's the wavelength of optical light, and so the wavelength is pretty small, depending on what you think is small, and it's fast. That's fast. I think by anyone's standards, that's pretty fast. 10 to the 15 hertz is pretty damn fast. So it oscillates really fast. But there's other types of light that a slower type of electromagnetic one would be microwaves. Microwaves. And so for microwaves, I have frequency is more like a typical microwave frequency would be 10 to the 10th hertz, much slower than light. That's 10 gigahertz, and they're much longer. A typical wavelength for that frequency, the wavelength is 3 centimeters. That's like an inch, a little more than an inch, so that's a pretty big wavelength. But then there are other electromagnetic waves that are even faster than light. A faster one would be X-rays. X-rays are really fast. For X-ray, I have a typical frequency of an X-ray is 10 to the 18 hertz, which then leads to a wavelength of 3 angstroms. And so that's a really small wavelength, and that's why X-rays are useful for telling us crystal structure, because the wavelength is on the order of the interatomic spacing. It's on the order of the interatomic spacing. And so so X-rays are very useful for probing crystals for that reason. Okay, so these are all different types of electromagnetic waves. And then, of course, there are many others too. You can go higher frequency gamma rays and lower frequency radio waves. But I just want to make that point. Okay, but the thing is that from a practical point of view, let's talk about something practical. From a practical point of view, something very practical are, for example, solar cells. And so we want to know how much energy am I absorbing in my solar cell. And so when we talk about the energy absorbing by a solar cell, then it's not useful to think of the time dependence. What we want to know is the average power absorbed. The average power absorbed by a solar cell. What is that average power? And so that's a really important question. And so what we have to think of is that if I have some solar cell sitting here absorbing power, if an electromagnetic wave is coming at it, then this is how you should think of it. You should think of it that I have this energy density is flying through space, where this is the electric field, and it's flying through space with some velocity c, and that energy density is being absorbed. It goes here with, that's the k direction, and it's absorbed by my solar cell. And so the solar cell, we can put it here at x equals 0. And so to calculate the power absorbed by the solar cell, the average power, that means these brackets means average, then I have to do a time average, which is 1 over t, because it's periodic. And so I go for 1 period, and I integrate from 0 to t, s of t dt. That is the average. That is the definition of average. I think you've seen that definition before. So that means then that if I want to calculate the power absorbed by my solar cell, I have to calculate as 1 over t times, and so now I have to do this integral, and the s is, I have to do the integral from 0 to t, where s is going to be c, the velocity, times the energy density. And the energy density is epsilon naught times E naught squared. But now I also have this part, sine squared. I'm sorry, what is going on here? Go away. Then sine squared of kx minus omega t dt. Okay, so I got to do this integral. But I can pick, but this part falls out. This part goes to 0, because I can pick x equals 0, the location. I can always pick x equals 0. And then the negative sign doesn't matter because it's sine squared. So this integral, the average power hitting my solar cell from light coming off of the sun, and is going to be this. And so this 1 over t, remember that's the frequency, nu, because frequency is 1 over period. And so the average power, actually I can already see that they're going to collide, so let's do it here. Average power is equal to the frequency of the light, and then I can pull, this part is constant, I can pull it out. That's going to be c, the speed, epsilon naught, the amplitude of the electric field, E naught squared. But then I got to do this integral, 0 to t of sine squared of omega t dt. I got to do that integral, where t is related to where I have where t is related to the frequency, because I have omega. I have omega is equal to 2 pi nu but nu is 2 pi over t. So I have this relationship between frequency and period that you've all seen before. And so now to do this integral, then let's use this integral. Let's use a little trig identity. Sine squared x is equal to 1/2 1 minus cosine 2x. And then we'll plug it in there. And so then we'll see that our power, our average power is equal to the frequency times c times epsilon naught e naught squared times now the integral from 0 to t of 1/2 of 1 minus cosine 2 omega t dt. Okay, and so then that's an easy integral to do, and so then that's equal to nu c epsilon naught e naught squared, and then that's going to be t over 2, which is going to be that part, and then minus 1 over 2 omega sine of 2 omega t, and this will be evaluated from 0 to t. And so then when you do this evaluation, then you see that I get nu c epsilon naught e naught squared, and this part turns into t over 2, and this part goes to 0, and you plug it in and see for yourself. It goes to 0. So that's really cool. So it's this little part right here that matters. That guy right there. That's the part that matters in the integral. And so I see then that these guys are hitting each other, and nu is equal to nu equals 1 over t, and so when they hit each other, they turn into 1. I mean, so then if I have nu times t equals 1, so then these guys cancel, and so I see that the average power is equal to 1/2 times c epsilon naught e naught squared. So that's the average power that I absorb. And so to get the average, this is the new factor. So the average power gets me that 1/2. And so then I call this the intensity. So this is the electromagnetic intensity that hits my hand, equals average power per area. And this is really important because that's the power per area, like you have a 60-watt light bulb, that's the 60 watts. That's the power per area that's warming you up when you're sitting under a light bulb. And then we can do the same thing for momentum. We can do the same thing for momentum, momentum density, because we can see that G is the momentum density. Remember, G equals epsilon naught E cross B is equal to the momentum density of any electromagnetic field, momentum density. But now we can consider the momentum density for an electromagnetic wave. And for an electromagnetic wave, we have these nice relationships we've just derived. And so we know already that G is equal to mu naught epsilon naught S. And so we can, what we see then is that we can write this as, for an electromagnetic wave, we can write this as really this is a general relationship, 1 over c squared s. That's the relationship between the momentum density and the Poynting vector. But now we can plug in our new expressions that we've derived, because now for a plane wave, we know that s can be written as the velocity times the energy density, epsilon naught e squared, and the direction, of course, is k, the direction of the plane wave. And so we then see that G the momentum density is equal to 1 over c epsilon naught E squared k. So, oops, but this is the unit vector, just the direction. So that's our momentum density. And so we can do the same thing for momentum density. We can now look at the average momentum density in space. We can say, what is the average momentum density in space? Because the momentum density varies with space and time. And we could do this kind of an average. We could do 1 over lambda times 0 to lambda of g of x t dx. We could look at the average momentum density in space. But of course, it's the same function. This is just going to give me the same thing. I'm going to get a sine. I'm going to get an E naught squared sine squared kx minus omega t. And so when you do your math, you're just going to get the same answer. You're just going to find that g, the average momentum density, is equal to 1/2 the magnitude of g, which is going to be which is just going to be where I'm just going to get this. So I'm just going to get that the average g is going to be 1 over 2 c times epsilon naught E naught squared, because that this integral is just going to give me a new factor of 1/2, which is what we just did a moment ago. So I can immediately just go from this equation to this equation without having to do any more math. We can just see that the average of this is just going to give me this 1/2, the spatial average. And we can even do the same thing for energy density, because we can see that the average energy density then in space is just going to be it's going to be the average of this quantity, epsilon naught E squared, but that's just going to be end up be 1/2 epsilon naught E naught squared. Okay, so I think you kind of see that pattern that is arising. And so, okay, so there's one other thing that I wanted to introduce at this point. So this, we can call it, so let's call this a breakpoint now. So this is a nice breakpoint. So you can leave now and come back at some other time to hear this next part. But I do want to, but now I will just say this next part. So let's just finish this train of thought. So the question we want to ask now is, what happens when an electromagnetic wave travels through matter? Travel through matter. You know what I think I'm going to do? I think I'm actually going to stop here, because I'm realizing that this lecture is going on pretty long, and so we'll do this next time. So that's what we'll do next time. Okay, bye-bye.